thank you all who are attended. It's a pleasure to see all of you in the beautiful city of Arcachon, virtually in 2D. And of course, I wanted more seriously to thank the organizers of the conference, for having kept the conference. I think we're all in need of exchange and interactions at the moment, and having managed to organize it in such a way that it's enjoyable, even if it's done by Zoom. Okay, so I've been instructed by the organizers to make a kind of survey, hopefully pedagogical survey, of the combined effect of disorder and interactions. I'll try to be pedagogical as much as I can. The audience is extremely broad, I would say, going from mathematicians to experimentalists. So please interrupt as much as you can. Don't wait till the end of the talk if you have questions. I think it's much better if you ask a question at the moment you have it. If you want to know more on the activity of the groups, I've given the link here to the group webpage, because I will cover various works, so I will be more limited on recent activities. And of course, you have at the bottom the sponsors that allowed us to eat during the research that we were doing. And of course, I'm a member of the Department of Quantum Matter Physics at the University of Geneva. Okay, I will of course talk of works which are coming from many other groups and results than my own, but concerning, I would say, my own work, I had of course the chance to collaborate with many people. A short subset is written here on the theoretical collaborations, and also we had the great chance concerning this combined effect of disorder and interaction to interact with various experimental groups. So I've put the two main side of interactions on the cold atom side with the lens group of Giovanni Modugno and Massimo Inguscio. And there were also experiments that I will tell very little about, which were done on the condensed matter side. And this was done with a group of Christian Ruegg at PSI, at the Paul Scherrer Institute in Switzerland. I've also put a couple of general references. I won't comment on these references, but it's just places where you can find more details, because I will skip most of the technical details on how to derive the results that I will present to you. There is a whole chapter on the combined effect of disorder and interactions in my book on 1D systems. There is a more recent review of modern physics, which recaps some of the more recent results. A couple of lectures given in two schools, which can give you more information, and more on the subject of many-body localization. There is a very nice recent review which has appeared in Review of Modern Physics. So I think with all these references, you can find most of the details that I will skip during this talk. Okay, time to start. So let me start with Anderson localization, and I hope I don't need to this audience to remind what Anderson localization is. But essentially, the main thing that you heard so far, mostly during this school, and in a way which is at the heart of the Simon collaboration, is the idea that one is looking at non-interacting systems. So in a way, it means that you have to solve a Schrödinger equation. So it doesn't matter whether it's waves originally, whether it's particles and you see them as wave through quantum mechanics. But the main idea is that you have to solve a Schrödinger equation, Schrödinger-like equation, which tells you that you have some differential operator here, which represents the kinetic energy. And then the particles are moving in a random or quasi-periodic, or you heard yesterday in Uli talk, or the day before in Jacqueline's blog talk, that one can be interested in other potentials than disordered. But the main point is that all this is working at a fixed energy, because you're working with a wave. You know perfectly well the energy of the wave, and that's the problem one has to solve. So the fact that the energy is conserved is a very important property, but it's a property which is only valid if you think in terms of particles when the particles are not interacting. And if I take a little example where I would say I have a chain of particles, so each side can be occupied or empty and particles can hop on the side. So this is what is called the tight binding model. Then if I have n sides and I have particles which are not interacting, essentially the size of the Hilbert space at a fixed energy is of size n. So you have to diagonalize n times n matrices, which of course can be an extremely complicated problem. And all the talks that came before showed you how complicated this problem is when this matrix has a random component or a quasi-periodic component. But the size of the Hilbert space itself is not growing too fast with the size of the system. And moreover, because the energy is conserved, it means you can define properties as a function of the energy. Hence, for example, the question of the existence of a mobility edge in energy. If the energy is smaller than a certain value, states are localized. If it's larger than another value, states are extended, and so on and so forth. And now all this collapses completely as soon as you put interactions in the system. So now let's imagine I have a certain number of particles in my system. 1, 2, this site is empty, 3 for this site. And now the particle can hop, but they also interact. And in that case, you see that the energy of one particle is not conserved because they can collide with the other particles and exchange energy with them. And moreover, it means that now, if you want to describe this quantum mechanical problem, you have to consider the full Hilbert space of the n particle together. You cannot just look at one particle. And now it's a different story because the size of the Hilbert space, let's say you get 2 possible states on each side, is not growing as n, but is growing as 2 to the n, which is, of course, a much, much, much faster growth. So as soon as you will deal with interacting problems, you are facing a huge growth of the Hilbert space, which make even clean problems extremely difficult. But if you add disorder, it also means that you will have to face this huge complexity coming from the growth of the Hilbert space size, but also the fact that now you cannot think in terms of measuring properties as a function of energy and so on and so forth. So in a way, you will have to find other probes to decide whether your state is localized, extended, what are its properties, which means you also have to reevaluate the theoretical tools that you have been using so far when you were dealing with what I would call non-interacting particles. Okay. This is not, of course, a new problem, and people have worried about disorder and interaction since a long time ago. And there was, in particular, a lot of activity on this problem in the 80s. And why? First, interactions in solids, you cannot escape them. Electrons interact with Coulomb interaction, and this is a huge interaction. So putting it under the rug was actually thanks to Landau, who told us that when you have fermions and repulsive interactions, we can sort of ignore them under a concept which is known as Landau Fermi liquid theory and think in terms of free excitations, which are called Landau quasi-particle. But technically, we cannot ignore interactions in a solid. And worse than that, if you put disorder, you can expect a strong interplay between disorder and interaction. Disorder, at best, will make the particle diffuse, so move much more slowly than before, which means the interaction effect would naively be strongly reinforced. And actually, this was something that was studied by Altshuler, Aronoff, and Lee in the 80s, showing that the interactions which were innocent in clean system became extremely dangerous if you had diffusive system, because simply particles were spending more time around each other. On the other end, if now you have more localized interaction, point-like interaction, not long-range interactions, well, if you localize particles in different portions of space, on the contrary, you would say the disorder is killing the interaction because simply the wave functions do not overlap anymore. And therefore, you can expect this very strong fight between disorder and interaction. So For fermions, this was studied in a variety of contexts, Altshuler-Aronoff-Lee by perturbative method, renormalization group treatment by Finkelstein. We did in 1D studies by renormalization with Heinz-Schulz. And this led to a host of physical effects that I don't want to enter into, like the possibility of forming electronic glasses, and of course, strong consequence on the transport property. I will more focus in this talk on the case of bosons. Why? Because for bosons, we know naturally that a very natural ground state of the boson system, when there are interactions between bosons, is superfluid state. Now, a superfluid, by definition, is something that is resistant to disorder. It should ignore the disorder, flow without being impaired by disorder. While if you have a localized state, you would say the disorder is paramount and has completely blocked the transport. So you immediately see that there should be this fight between interaction between bosons that promotes superfluidity and therefore should give you excellent transport, and localization effects that would like to kill the superfluid state. Moreover, for bosons, the free boson solution is completely pathological. And let me try to explain this very rapidly. If you have free bosons, and let's say you have a random potential here, such that there is a region where the disorder is at a value, let's say, minus V0 here. If you put one boson in this region, its wave packet will be localized here. So you lose in kinetic energy an amount which is proportional to P squared over 2m, and P is of the order of 1 over L by the uncertainty relation, but you gain an energy V0. So you can always find a rare event where you will find a region which is large enough so that this is a gain, which means you will put one boson in this region. But because they are free, if you can put one boson in this region, you can put all the bosons in this region. So you see immediately that this type of rare event gives you a state in which you can put an infinite number of bosons in a finite region of space. So the density in the thermodynamic limit would be infinite. Any infinitesimal interaction will make this state explode and go to a much more uniform solution. So if you want to deal with bosons, you need to include interaction from the start. So all this was to motivate a little bit that this question of combined effect of disorder and interaction is a problem which is extremely relevant in a large variety of systems, but B, of course, a problem which is incredibly rich and incredibly complicated. And for that, we need all the technology that we have, both on the theoretical level and on the experimental level. So let me continue and take as an example the localization of 1D interacting bosons. Just to fix what I am looking at, I will look at, for the moment, systems which are purely quantum mechanical. So I put myself at 0 temperature, I don't have any temperature, and I will just look at the phase diagram, at the various phases that I can realize in the system. So here is the problem. I've written it in what I would call first quantization language. So the Hamiltonian of the system is P squared over 2m for each particle, the kinetic energy. Then, of course, you have the interaction between the bosons, which depends on the position of each particle. Typically, people take a delta function interaction, but it's not necessary. You can put any type of interaction you want here. And then you have the usual disordered potential, which couples to the density. So let's say this is the density of particle at the point Ri, or this is the strength of the disorder, rather, at the point Ri, where the one of the particle is located. So this looks like an innocent problem, but as we discussed before, this is an extremely complicated problem. If the last term is not there, this would lead to superfluidity if you have bosons at 0 temperature. If you didn't have the interaction term, as we discussed, you would have this pathological state, but essentially this is standard Anderson localization. And of course, the question is, what do you get if you have the competition between this interaction and this disorder? So this was a problem that in one dimension, we could solve a long time ago with Heinz-Schulz using techniques that I don't want to discuss here, which are known as bosonization and field theory and so on. And I will show you the result in a moment, but there are two things that one should take out of this solution. The first one, there is indeed a competition disorder versus interaction that I will show you in a moment. And second, there is the existence of a new phase, which is a localized phase, but which is now many-body, where all the bosons are interacting with each other. And this is this soup of boson, which is localized, and this phase was nicknamed the Bose glass for obvious reasons. Okay, so let me show you the phase diagram. So I will take two axes. One is the axis of disorder here. The other is the axis of interaction. So I have bosons. This is the strength of the repulsion between bosons. Let's say they interact with a contact interaction. They repel each other. They lose the energy U when they are on the same site. And this axis is the strength of the disorder. So if I have no interaction, every state is localized. We have the sort of Anderson localization, but as I said, maybe a little bit more pathological for the bosons because they all go in the same localized state. And now when you put interaction, what you find is that there is this very strange boundary, which is here drawn in a totally schematic way, where you have a dome here, which separates a superfluid phase. So in this region, which is marked superfluid, interactions between bosons have completely erased the effect of disorder. Anderson localization does not exist. The system is as good a superfluid as if it had been a clean state to start with. In 1D, a true superfluid does not exist, but it means you have power law decay of the superfluid correlation functions. And then you have another phase, which is on the top of the dome here, where states are localized. Here, I drew them as if they were localized one by one, but of course, this is not correct, and you should think of this phase as really a many-body phase, where the combined effect of the interactions and the disorder produce a state which is globally localized, and I will tell you how you can decide that it's globally localized. And this is the phase that has been nicknamed Bose glass. So you see that, for example, if you work at constant disorder, interactions have first a delocalizing effect. They promote the superfluid. But then if you increase them too much, they will have a relocalizing effect where they will destroy the superfluid to put you inside the Bose glass phase. And there are still many questions on this phase diagram that people address that I don't want to go into, whether there would be two different localized phases and a line which would separate them and so on and so forth or not. But at that stage, I don't want to discuss these points, just to show that there is here an effect where, contrarily to single particle solutions, the interactions are able to erase completely the effect of disorder, or on the contrary, depending on the strength of the disorder. Here you see that in this region of interaction, again, even an infinitesimal disorder is able to destroy the superfluid. Not plane waves, but a state which normally should have been a superfluid, so able to flow without dissipation. Now, Marcel, I saw that you raised a hand.
Yes, is this a zero temperature picture, or is
Yes.
it valid for, okay.
Okay,
and
so
how far does it hold this picture?
That's a very good question. So at the moment, this is a zero temperature picture. I'm talking about ground state at zero temperature. The question of finite temperature, we'll come back to it in a couple of minutes. And one of the very, very interesting question, an open question at the moment, is how, if I put the axis of temperature on this phase diagram, this picture is holding. 15 years ago, I would have told you, as soon as you put temperature, well, you get finite conductivity in the localized region. Now, maybe this picture is robust even up to a threshold of temperature. And this is what people call now many-body localization. I'll come to that in a moment. So ask me again when I discuss the finite temperature effect. But for the moment, what I'm showing you is the zero temperature result. Are there?
There's a question in the chat.
Yes, I don't see the chat, so you will have to, yes, chat, I can. Is a superfluid phase, what does the ground state and the first few excited state look like? Okay, so in the superfluid phase, the system has, of course, okay, in 1D, it doesn't have an average of the single particle creation operator because it's 1D. But essentially, this is a state where the excitations are sound waves of fluctuations of density, just like in a normal 3D superfluid. And these excitations have a finite velocity, again, like if you were doing Bogoliubov mean field theory in a 3D superfluid. So I don't know if it answers the question or not. So this superfluid phase in 1D technically is called a Tomonaga-Luttiger liquid. So it has excitation that are sound oscillations of the density.
Fine. Okay, you can.
Yeah. Okay, so
you can go on.
I continue. Okay, how do you decide that the phase is localized? Okay, now I need to re-click somewhere there. Well, you cannot use again a criterion. So you compute, for example, the average of the single particle correlation. So you try to create a particle at point 0 and then destroy it at point X. And in the superfluid, this correlation would decay as a power law or simply go to a constant. It would be 2D or 3D. But in the localized phase, you would find that this correlation, again, it's a many-body correlation, not looking at one particle specifically because they're all indiscernible, decays exponentially with a localization length here that you can identify with the localization length of the system. If you were looking at the particle one by one and non-interacting, this object would be a function of the energy at which you're looking at. Here, it's just a function of the global system that you are looking at. You could also compute the conductivity of the system. We'll come to that and look and see that this conductivity tends to 0 when the size of the system is going to infinity. Okay. If you're on a lattice, this is a little bit more complicated. I don't want to go too much into detail. So far I was discussing bosons that would exist in a continuum. If now you really impose a strong lattice to exist, then you know that you can have various possibilities. For example, here in this lattice, I've put one particle per site. But if I try to put a second particle, I pay a repulsion U. So it costs a huge energy. And then this phase will be incompressible. I will not be able to add particles by changing the chemical potential of the system. dN d mu is 0. And this is a phase which is known as the Mott insulator. And this is a phase which, of course, has no superfluid order. So the average of the single particle wave function is 0, or in 1D, it means that this correlation that I showed before decreases exponentially. So this is a tough insulator. This is the Mott insulator, incompressible. We have, of course, the superfluid. I shown here a kind of disordered potential, but let's say we're in the superfluid phase. In the superfluid, everything is phase coherent, but you can also add one particle at very negligible cost. So the system is compressible, dN d mu is finite, and of course in 2D, in 3D, let's say this would have a finite average. In 1D, the correlation function decay as a power law. And then you have the Bose glass where particles are localized. Again, the drawing is misleading. It's not individual localization, but I don't know how to draw it better. And you can still add a particle at 0 cost. So this is a phase which is compressible, but which has no superfluid order. So you see a little bit the three possibilities that you have to have superfluid, compressible with phase order, Bose glass, compressible without phase order, and Mott insulator, incompressible without phase order. And again, these phases have been studied by a large number of people, by a large number of methods. Okay. If you want to confirm that the solution we got is correct or not, or more generally study these problems, of course, Numerics has proven to be an invaluable tool. And you hear, I'm sure, much more, not on this particular problem, but on the problem of MBL in the talk of Nicolas Laflorency. Here, I'm showing one phase diagram that was obtained a long time ago by Uli Schölvöck. And you see, this is the strength of the disorder. This is the strength of the repulsion. And now, why don't you see exactly what I showed before? Because now they are on a lattice, and this is needed in a way for the numerics. So the Mott insulator is coming to pollute a little bit the phase diagram, but you see this reentrant superfluid phase separating two regions, which are Bose glass, and the Bose glass versus Mott insulator is determined by the criterion that I gave you before. So this is a very interesting state of matter where, again, this is combined effect of interactions and disorder that leads to this phase where you get both localizations, but also collective effects. Now, of course, this was for true disorder, but now you can ask the same question that was asked for non-interacting system. What about other potentials? For example, the biperiodic potential that you heard, I guess, in talks of Jacqueline and talk of Uli. Okay, Uli had more beams, so this was even a more complicated version. But taking two periodic potential, but with irrational commensurability between them, this is the so-called Harper potential. And we know that for non-interacting system, if the interaction is zero, and you make one of these potential very, very large so that you can describe this first thing by a tight binding Hamiltonian, the second potential leads to the Aubry-André model, where there is a localization transition when the weaker potential is equal to twice the hopping on the side. Well, if you put interactions, the question is, do you keep this physics? And is it looking the same as true disorder? So this is a little bit more complicated, actually, paradoxically, to study. One can use RG techniques, and this is something we did a long time ago with Julien Vidal and Dominique Moana for Fibonacci potentials. For Harper potential, actually, you have to use numerics. Here is a simulation that was done.
You have a question on this chat. I'm
sorry. I'm not monitoring, so don't hesitate. Nicolas says, I agree. And now I have to go back to the, in the superfluid phase in 1D, shouldn't the average of the field be zero? Yes. So yes. And in 1D, how do you distinguish? So it's not because the average is zero or non-zero, but it's the way the correlation function, so psi dagger, psi of x, psi dagger of zero, decays. In the superfluid phase, it will decay as a power law. In the, sorry, so let me go back a little bit. So in the superfluid phase, here, the correlation function that I've shown here decays as a power law. In the Bose glass phase, this correlation function decays exponentially. And at the transition, by the way, the exponent is universal. And this is very reminiscent of a Berezinski-Kostelis-Thouless transition. A little bit different, but essentially it's the same spirit. So in 1D, you don't have a true order. So the average is always zero. But by looking at the nature of the decay of the correlation, you can distinguish between the superfluid and the Bose glass phase in an unambiguous way, because there is no way you can smoothly go from a power law to an exponential decay. I hope it answers the question. Okay, super. Okay, so let me move back to what I was saying. Okay, so here is the same phase diagram that I showed for the disordered case, but this time for the Aubry-André model. V2 is actually what I call V1, sorry about the notation in the above potential. And here is the axis of disorder, if you want, or quasi-periodic type of disorder. And this axis is the interaction. And you see a phase diagram which actually is very similar. Okay, there are little differences. This is more amoeba-like and whatever. There are directions which lead to resonances, but essentially you see the same type of qualitative feature, that there is a phase where interactions make the system superfluid enough to resist the external potential, and then a region where this external potential fights the interaction well enough that it leads to the Bose glass phase, or a phase which you could give a different name because now it's a quasi-periodic system, but which has essentially correlation function that decay exponentially, like for the case of true disorder. And you see again that the Mott insulator, which is the fact that you can get a commensurate potential, eats a part of the phase diagram. It depends a lot on the filling that you put. This is for one particle per site, but if you were putting another number of particles per site, the topology of the phase diagram is a little bit different. The Mott insulator phase does not exist, but you see again that you get this sort of coexistence between the superfluid phase, where the system is robust to disorder, and the Bose glass phase, where again you get a many-body localized phase due to the quote disorder. So I would say biperiodics or true disorder, from that point of view, they look close enough that one can safely use biperiodic potential or quasi-periodic potential. In these other works, we were looking at Fibonacci sequences to study also this type of problems, which of course makes it very convenient because cold atom experiments are mostly done with this type of potential when there are interaction presence. Okay, so people started to hunt for the Bose glass, and I won't go into all the experiments that were done, but there were the old experiments which were done in Josephson junction arrays. There are, by the way, very interesting new experiments which are done in particular by the group of Doty in Australia. There were wonderful experiments in the group of Alan Goldman on films, where you see very clearly that when you lower the temperature, you get a phase where the resistance is going to zero, and a phase where the resistance is going to large value, which seems to indicate a superconducting insulator transition. And people tried also to inject helium in porous media. This was much more complicated. But of course, now we have new remarkable systems, and cold atoms are, of course, remarkable systems, and I will mostly insist on those. There are new superconducting films. Here you see interfaces between two insulators, LAO and STO, which leads to 2D superconducting superfluid phases. So this can also be used to study disorder. And one topic which I will not discuss at all, much to my regret, but this is a question of time, which is disorder in spin dimer systems, because actually spin 1/2 is isomorphic to a hardcore bosons. You can say if the spin is down, I have no boson. If the spin is up, I have one boson, but I cannot get more than one boson per site. So actually you can use these systems to do experiments on hardcore bosons. And there is a wonderful set of properties that you can use. This was done mostly experimentally in the group of Christian Ruegg at PSI, but there are many other groups in the world, Los Alamos and Japan, who were looking at these systems. If you want to know more on what one can do with this, I refer you to this review article. But the thing which is interesting is that you can disorder this system by doing things to the solid, and there are fantastic laboratory also to study this effect of combined effect of interactions and disorder. But let me insist on the cold atom systems. And here is a class of experiment that was done in Florence. And there are various incarnations of this experiment. So this was done mostly in the group of Giovanni Modugno. So by using lasers, you divide the system into 1D tubes of bosons. And then in one direction, you put two sets of lasers. So you realize the biperiodic potential that we were discussing before. And we helped a little bit on the theoretical side. So the theory was done mostly by Guillaume Roux and Thomas Martel, because in order to compare with the experiment, one needs to do extensive DMRG, so density matrix renormalization group calculations, both at 0 temperature and at finite temperature. So here is the result of looking at such systems as a function of, again, the disorder here and the interaction. And what is plotted here in color code is actually what is called gamma, is the width of the Fourier transform of this correlation that I showed you. So when you have an exponential, the Fourier transform is a potato. And if psi is small, the Fourier transform is broad. When you get a power law, the Fourier transform is extremely sharp. This is the superfluid, if you will. So when gamma is small, you would say it's the superfluid. When gamma is large, you would say it's localized. And of course, one needs to quantize this a little bit more, but just give you a flavor of the phase diagram. And here you see this phase, which you would like to identify with a superfluid. And you see this type of phase that you would like to identify with the Bose glass. And so you see that experimentally, this experiment is perfectly in line with what you would expect. At 0 interaction, because it's a Aubry-André model, not a true disorder, you need a threshold of, quote, disorder to get the localized phase, which is, again, in agreement with what you would expect. So these experiments are wonderful experiments because they sort of are clearly a good experimental realization of the type of physics we were discussing. They suffer from a drawback, however, which is that the temperature in this experiment is a little bit high to make comparison with a 0 temperature phase diagram. So let me show you here. This would be the full Fourier transform of the correlation function in the superfluid region. Actually, I forgot the value of the interaction. I think it's written here. It's 2.3. The blue is the theoretical calculation of the width coming at 0 temperature for a single tube. The red is what you get in the system at the temperature of the experiment for the average over all the tubes. You see it's considerably broader, but we can compute it very accurately by the DMRG procedure and doing the average over the tube using local density approximation. And the black line is the experiment. So you can say that we have a very good agreement between theory and experiments, but we need a lot of theory to deconvolve in a way all the effects of temperature and averaging over the tubes. So it would be fantastic if the experiments could be done at a lower temperature to be able to compare. Now, temperature is actually pretty low in the experiment. The problem is that because they wanted a first lattice, which was very high to be in the tight binding limit, to have the Aubry-André model, it kills the kinetic energy. So the ratio of kinetic energy versus temperature is actually not so high in this experiment. The solution would be to say, let's lower the first lattice. But then you don't have an Aubry-André model, and you don't even know if it gives rise to localization. So this is a problem that we looked at recently on the theoretical side, together with Epeng Yao and Laurent Sanchez Palencia at Polytechnique, which is to say, well, instead of taking a huge first periodic potential plus a small perturbation, let's look at a potential, a biperiodic potential, where the two terms would have the same amplitude. And the question is, of course, does it lead to Bose glass? Does it lead to a localized phase? And I don't want to go into too much details on this discussion. I refer you to this publication. But here is the phase diagram This axis is the repulsion, which increases when you go to the left. The vertical axis is the chemical potential. And this is for various strength of this potential here. And you see very well that you still get possibility of getting a Bose glass phase, even if you don't go into the limit, which would canonically give you the Aubry-André model. So using this, it's probably possible to use the same experiment to go much closer to what would be the zero temperature phase diagram.
Well, you are about 40 minutes, Thierry.
Perfect. Yeah, we'll move very fast on the transport, because of course the other way to decide whether a phase is localized or not is to measure the conductivity. So you can measure two things. One is the AC conductivity, the one which responds to an oscillating signal. And I'll just show you what it is. I won't discuss the shape. It's something which has a maximum at a scale which is essentially inversely proportional to the localization length. So observing this kind of thing, and in optical lattice, it can be done easily by shaking the optical lattice or shaking the trap if you're in a trap. I think it would be a very interesting way to probe finely also for the physics of this localized state. Okay. This power law is non-universal here, and this power law is universal here, but I don't want to discuss it too much. Now let's finish with the thermal effects and to address the question of Marcel. What happens if now one puts the temperature? And the answer is, well, it depends. If I want to look at DC transport at finite temperature, let's look first at non-interacting systems. In 1D, all states are exponentially localized. And when you put a finite temperature, the only thing you do is an average over all these states with a weight, which is essentially the Fermi or the Bose factor, as a function of the energy. But you're averaging zero for the conductivity. Every conductivity is zero. So at finite temperature, the conductivity will stay completely zero. So if you were looking at a non-interacting system, the conductivity would stay zero at any finite temperature in one dimension. And of course, this is a little bit shocking because we are used to having finite conductivity at finite temperature, but this is simply because your system is completely isolated, and the temperature is not imposed by exchanges with the thermostat that allows you also to exchange energy. So if you want a finite conductivity at finite temperature, you would need coupling to a thermal bath. Or one question is whether with interaction, the system could be its own thermal bath. One particle sees the rest of the particles as a kind of thermal bath. Now, with a bath, the situation is relatively simple because you can compute the conductivity and it gives some finite conductivity. I don't want to discuss it here, but you see here a conductivity that diverges with temperature in the superfluid phase and would go to zero in the localized phase. Down in the localized phase, it's difficult to compute the transport. And again, this is a difficult question, but this was addressed by Mott. There is a theory which is called Mott variable range hopping that I can explain, but let me skip this explanation for the moment. It's a nice compromise by saying that you have to hop from one localized state to another localized state, and the energy difference between these two states is absorbed by a bath, which is your thermostat, which is able to give you or take back energy from the system. At the end of the day, it gives this very nonlinear dependence of the conductivity as a function of the inverse temperature. Beta is the inverse temperature with an exponent which depends on the dimension of the system. So this is what is called variable range hopping. In 1D, one can again do the calculation. This is what we did with Thomas Natterman and Pierre Le Dussal, and sort of derive cleanly this Mott law, taking into account the interaction. This is for non-interacting systems. And you see, you recover the beta to the power 1/2, but now the prefactor correctly incorporate interactions and disorder. But this is with the thermostat. If you have no thermostat, the prefactor here vanishes, and then you have to find what is going on. Without a bath, the question is again, can particle be a bath for the others? And can the system even reach thermodynamic equilibrium? Because now you have no bath, and explore ergodically the phase space. And this is what has been known recently under the name of many-body localization, which is this very question that was asked by various people, Basco, Alainer, Altschuler, Gorny, Mirlin, Polyakov, David Hughes, and in the dot hides dozens and dozens of theorists. So I send you back to the review paper of Dima and Ehud, Emmanuel, and Maxime Serbin if you want more detail. But let me just give you the conclusions, which I think don't take them as written in stone, because people are still hotly debating. But the idea would be that if there is no thermostat, the T equals 0 physics is still true. So sigma of T would stay 0, for example, as long as temperature is below a certain threshold. So in answer to your question, Marcel, the idea would be that my T equals 0 phase diagram could carry out without problem up to a finite temperature. And then things would start to be always conducting, whether I'm in the superfluid or whether I am in the quote localized phase, of course, with very different amplitude for the conductivity above this threshold. And the second conclusion, which is interesting, and you'll hear much more about this, I guess, in the coming talks, is that the system is not ergodic, it doesn't explore all the phase space that it has theoretically at its disposal, even at finite temperature and energy. And this is something we know for disordered systems, and for many disordered systems, there is a physical phenomenon which is called aging, which is the fact, here is one case which was studied in a so-called Wigner crystal, quantum glass. You get a solid which has phonon-like excitations, you put disorder, and you're wanting to know how the system reacts if you change brutally its chemical potential. How does the density changes? And you find that this response is not invariant by translation in time. The system remembers for a very long time that you prepared it in a given state at time 0. And this phenomenon is known as aging, and this is reflecting the non-ergodic nature of glasses. The observables depend on time. How this phenomenon is linked with the phenomenon of many-body localization that people want to address now at very high energy, this is an open question that I think will need certainly much more studies to be answered. Okay, on that, I will conclude. So I would say there are several take-home messages. There is first this remarkable interplay between localization and interactions, which needs to be explored and which is a very, very difficult problem. It's a fantastic challenge, both in equilibrium. I call it localization of interacting particles, so that just the words are not colliding, but also out of equilibrium, which now is called many-body localization. But I want to emphasize that all this is many-body localization. It's localization of many-body systems. And there are also now experimental possibilities to explore this phenomena, both with cold atoms and to some extent also in condensed matter. And finally, one final conclusion is that we need better tools. Both our analytic and theoretic and numerical tools are limited, and to really understand this extremely complex system, we need, of course, to think a little bit harder. And on that, I'll stop, and I thank you for your attention.
Okay, thank you, Thierry. It was good that there were questions during the talk. Marcel is applauding. Okay, I think everybody is happy with your talk. Nicolas Laflorenzi has a question. So Nicolas, switch on your microphone, maybe.
Yes, hi Thierry, thank you for
Salut, Nicolas.
Yes, so I have a simple question. So when you say that the conductivity should be 0 up to a finite T star, I'm wondering, because if all the eigenstates of the interacting disordered system are
okay, so first, I'm not sorry to cut you. I'm not saying this. Alainer, Basco, Altschuler are saying this.
Okay, because that implies a mobility age, right? Because if all eigenstates are localized, probably sigma should be 0 at any temperature.
So I think you should take these 2 points as with big question marks here.
Yeah.
And I'm just pointing out that before all these excitations on many-body localizations, people would have said, as soon as the temperature is finite, the conductivity becomes finite with Mott variable range hopping, for example, type of law.
Right.
And
Yeah.
what these people want to claim is that, no, it's not completely true. Instead of having an exponentially small conductivity, which would occur certainly if you have contact with the bath, with the thermostat. If you don't have contact with the thermostat, then the system could retain a conductivity which is 0 up to a finite temperature. And this was the claim which was in their first paper, in the Basco-Alainer-Altschuler paper, where they were doing an expansion in interactions around the non-interacting solution. Whether it's correct, whether there is a small exponential tail or whatever, I think at the moment the dust is still in the air.
There is another question by another Nicolas Cheroré.
Yes, hello, thank you very much for the talk. Just a question regarding the experimental phase diagram of the Bose glass superfluid. So there's apparently absolutely no trace of the Mott insulator, although this is in a lattice. So is it because the mean occupation number is not well defined?
Exactly. So here is the line which would be the theoretical limit of the Mott insulator. Now, of course, as you pointed out, it's not totally visible that there is something like this. But here we are facing the usual problem, and all the people who have heard me mention this in cold atom context know how much I hate the parabolic trap and how much I would love boxes. And one of the reasons is that here, of course, you could say you get 1 particle per site in the central tubes, but as soon as you move away, the filling is not 1. So you get a soup of coexistence of Mott insulators with other phase and so on and so forth. And that's why you don't see particularly the Mott phase, but this is above, let's say above this line. The physics is much more dominated by Mott physics than by the quasi-periodic aspects of the system.
So you should be happy because there are more and more experimentalists with box potential. So
yes, I am.
Okay, so if there is no more question, no, I don't see anybody else.
I had a question, Alain, sorry.
Ulrich. Okay.
I raised my hand, but maybe it's only you.
No, I was checking the chat because it seems that everybody was asking questions on the chat. So
okay, sorry, too many ways to communicate here. Yeah, Thierry, thank you very much for this very nice talk. I have a question about what you mentioned about the optical conductivity. Were you plotting there the real part or the imaginary part of the conductivity?
So this was the real part, but we can also compute the imaginary part, of course, as you can imagine. So this is the real part. Sorry, I'm trying to go back to the. No, this is after, I guess. Blah blah. Yes. So this is the real part, and of course it has to go to 0 because the static conductivity is 0. But the interesting thing is that it has this maximum. Here, the imaginary part will be the Kramers-Kronig transform of this one as it should.
Yeah, because I'm just wondering whether there is a way to measure the real part in the experiment. So normally,
well, again, technically, if you measure the imaginary part, you get the real part. So here, it's true that this is my reflex, I would say, as maybe a more condensed matter training. But we can give you the imaginary part. Indeed, if you shake, the most easy to measure is the imaginary part. But one can be deducted from the other by Kramers-Kronig transform.
Okay, I see a hand raised by Li Chen. Is it that he forgot to lower his hand, or do you have a question, Li Chen? He has a question. Okay, go ahead.
Thanks for the talk. Do you mind going back to one of your diagrams where you have the phase diagram from, superfluidity, Mott insulator, and I was wondering, I didn't see the.
For example, this one, yes, or
is there something like a triple junction? Because I was wondering if you just look at the order.
Hello. I think there was a cut. At least I do not hear you anymore.
Oh, sorry, I got muted somehow. I was wondering if you look at the order parameter in the superfluidity phase, and if you just follow it as it goes to either the Mott insulator phase or the Bose gas phase, if you somehow sort of normalize this order parameter in some way, can you see the order parameter, going to different phases, like rather a localized phase or one that's less more coherent kind of spread out thing as you move between these three phases, especially near if there's a triple junction?
Okay, so there was a big debate at some point how the topology of the phase diagram should be, and maybe for that I will go back to this one. And in particular, whether there could be a contact between the Mott insulator and the superfluid. And you can show relatively convincingly there were various degrees of proof, I would say, that there must always be a sliver of Bose glass between the Mott insulator and the superfluid. So in a way, at least theoretically, there is never a triple point which will contact the three phases.
Oh, okay, thanks. So
you see it here on this numerical, but it's not a proof. But you see that the Bose glass is sneaking here in between the Mott insulator and the superfluid.
So is this a general phenomenon, or there might be pathological?
No, it's a general phenomenon. It's just because imagine the Mott insulator would stop to become the superfluid. It means the gap of the Mott insulator is very weak, and then in a way it becomes sensitive to the disorder. So at the boundary between the Mott insulator and the superfluid, the disorder is relevant and sort of puts the sliver of Bose glass. There are various ways to prove this. In 1D, you can prove it by renormalization using the methods we developed with Heinz Schulz. In more dimension, there is a very nice paper by Nikolai Prokofiev and Boris Vistunov using what they call the inclusion theorem, which is to imagine the effect of disorder on a subpart of a phase that would be Mott insulator with a very weak gap. But I think it's pretty convincing now that you always get a Bose glass phase in between the two. Now, maybe with more exotic potentials, one could imagine a triple point. But with the disordered systems, I would say the Bose glass sneaks between the other phases.
I see.
Okay, thank you. I think it will be time to stop. So thank you, Thierry. We have learned many things. And at the end, we have learned something very interesting. Normal magician hide cards in sleeves, but you hide cards in a Bose glass sleeve, right?
I had them on the desk. So
yes, and do you hide them in a Bose glass, Thierry?
Always, but they are very localized. So.